Almost 20 years ago, high above Antarctica, NASA's balloon picked up a signal, a sharp radio pulse from deep beneath the ice. Maybe a fluke. But then in 8 years, another one came. What's going on? This balloon was part of the Anita experiment, which wasn't supposed to hear anything like this, especially not from that direction, especially not twice, as if something underneath the ice itself had suddenly decided to speak. Of course, experts across the world were called in and found somewhat plausible explanations from our current understanding of physics. But as years went by, these theories were stretching thin due to new data until we had nothing left except the mystery itself. So today, let's swoop into the 11th hour and try to crack the Anita anomaly. What exactly broke from beneath the Antarctic ice and why it might be a complete game changer for science. You might have seen those headlines, unexplained radio signals coming from beneath Antarctica and so on. Unsurprisingly, it fueled quite a lot of speculation online. UFOs, frozen pyramids, secret German bases from World War II, etc. Some people went full Atlantis, suggesting the radio signal came from a lost civilization, frozen for 10,000 years. But before we go digging for ancient bunkers, let's back up a bit because the truth is weirder. First off, you need to know that the Anita experiment is not some secret military project. It's a giant science balloon. Between 2006 and 2014, several of them were launched as high as 35 kilometers above the South Pole with a rig of antennas hanging below it like a chandelier built by nerds. And it wasn't giving out free Wi-Fi. Anita is designed to detect neutrinos. These particles are really weird. They have no charge, almost no mass, and they pass through almost everything. Your body, the planet, even stars, without leaving a trace, and they do so in billions each and every second. You physically can't notice that. Imagine firing a bullet into a swimming pool and missing every molecule of water. That's a neutrino. Most of them come from the sun, but Anita wasn't looking for those. It was hunting monsters, ultra-high-energy neutrinos, some of the rarest and most powerful particles in the universe, usually produced by supermassive black holes consuming matter, quasars. And when one of these things actually hits something, it can trigger a tiny particle explosion, a cascade of electrons in the ice. That cascade in turn emits a burst of radio waves, like a tiny crackle of thunder called Asgardian radiation. My God, that sounds otherworldly, but that's exactly what Anita is designed to catch, radio echoes of absurdly rare collisions inside the frozen continent. Normally, those signals come from above or maybe from the sides at very shallow angles. Basically, a neutrino flies in from space, smacks the upper part of the ice cap, and sends a radio wave bouncing upward to Anita's antenna floating overhead. Case closed. But that's not what happened here. It's called the Anita anomaly because those two signals in 2006 and 2014 didn't come from above or from the sides. They came from below, as if particles that produced them came directly from beneath the ice, and that made physicists go pale. If those pulses really came from a high-energy neutrino, that means it entered the Earth on the North Pole, traveled through thousands of kilometers of solid rock, and then hit the ice in Antarctica. Now, that is so weirdly specific. It would be the same thing if you ended up in a war zone and ran through thick gunfire and artillery shelling for miles, and then got hit by the very last bullet. It just doesn't make sense. Too much of a coincidence. And mind you, we have two of those. A funny thing is, from the scientific perspective, a secret alien base with a broken radio would have made much more sense. It's just that Anita wouldn't hear it because it's fine-tuned to neutrino signals. So there's our mystery, and physicists swooped in with possible explanations, and the first thing on their minds was, what if it wasn't an ultra-high-energy neutrino, but something rare and even more powerful? It was the night of October 15th, 1991, in the Utah desert. A team of researchers was running the Fly's Eye experiment, an array of telescopes designed to watch the sky for faint flashes of ultraviolet light. Routine work, quiet night, until one detector registered something wrong. At first glance, it looked like some malfunction, but then the scientists checked the numbers and their jaws dropped. It was a single subatomic particle, but it had so much energy that it didn't seem real. We're talking numbers with 20 zeros, millions of times more than expected from the boldest predictions. This particle hit the atmosphere carrying more energy than a 100 kilometers per hour fastball, except this most likely was a proton, something a billion times smaller than a speck of dust and yet as energetic as a speeding baseball. And one scientist finally said what everyone was thinking. Oh my God. That name stuck. The oh my God particle to this day is the most energetic cosmic ray ever recorded. It lit a fire in the physics world because it proved the universe could hurl a single particle at Earth with an energy we barely understood. The oh my God particle wasn't supposed to exist, but it did, and we're still not sure how to explain it. Even supermassive black holes don't cut it. So when Anita recorded its strange upward signal, some wondered, could this be another moment like that? Another ultra-rare cosmic ray just slamming into the Earth in some bizarre trajectory? At first glance, it made some sense. Cosmic rays are notorious for their energy. They can trigger Asgarian radiation just like neutrinos. They can cause huge particle showers. They are fast, chaotic, and poorly understood. All the ingredient of a good mystery. But there was a problem. Cosmic rays don't sneak in. They crash the party. That's their whole personality. They come from outer space, slam into the atmosphere, and explode. If one tried to enter Earth from the opposite side through the mantle, the crust, the core, it wouldn't make it, not even close. Even the oh my God particle, the strongest cosmic ray ever recorded, would have been vaporized halfway through planet at best. It would never hit the ice on the other side like nothing happened. And that's exactly why the ultra-high-energy neutrino couldn't plausibly do it as well. When the particle is at overcharge, the probability of it interacting with dense medium-like rock and even the relatively thin atmosphere skyrockets. So, as thrilling as the idea sounded, it didn't hold up. The oh my God particle was incredible, but it was still a cosmic ray. Anita's anomaly walked like one, talked like one, but it couldn't have been one. And after all, even in 1991, physics held firm. The oh my God particle didn't break the rules. It just pushed them to their limits. Anita's anomaly, that one still looks like it's cheating. So maybe, just maybe, we're dealing with something science hasn't officially met yet. So we have to chase the edges of known physics itself. Actually, for the past couple of years, the leading theory on the Anita anomaly stated that it could have been some exotic types of neutrinos. And to meaningfully approach that, we first need to understand the basics. You see, as early as in the 1930s, scientists noticed that certain radioactive decays didn't conserve energy. Something was missing. And then Wolfgang Pauli proposed a bizarre idea. What if there's an invisible particle, electrically neutral, nearly massless, and impossible to detect, that carries away the lost energy? At the time, it was a desperate guess and frankly just a clutch to keep formulas working. But then surprisingly, we indeed found those elusive particles, and they became essential to the standard model of particle physics. So far, we confirmed 3 types of neutrinos: electron, muon, and tau. But the really odd thing about them is they can oscillate or switch identities as they travel. Imagine a K-pop band of 3 where each member changes from concert to concert, but you can't tell the difference because they can switch only between 3 archetypes, except sometimes, very rarely, you can sense they break the pattern. When Anita detected a radio pulse coming from below the Antarctic ice, the first idea that really stuck was that it came from a tau neutrino. In theory, here's how that would work. A high-energy tau neutrino enters the Earth on one side, travels deep underground, and somewhere along the way, it transforms into a tau particle, a heavier, unstable version of itself. That tau particle then travels through the rock, collides with some atom, and decays back into a tau neutrino or, much more likely, a shower of them with lower energies. One of those final tau neutrinos hits the Antarctic ice, triggers a particle cascade, and Anita picks up the Asgarian radio signal. Boom! Here you go. We essentially caught our K-pop star turning into the sumo wrestler and back. A huge media scandal ensues. So yeah, it's a bit contrived but clever and seemingly fits the picture. In fact, experiments like IceCube and the Pierre Auger Observatory actively search for this kind of tau regeneration. It's not fantasy, it's real physics. Meanwhile, some theorists propose that it could be something even stranger, something we've never actually seen but that theorists have been whispering about for decades. The sterile neutrino, the 4th and most mysterious member of our K-pop collective. Now, this one is not part of the standard model, just a proposed extension, an attempt to explain all the weird inconsistencies we found in various neutrino experiments. Sterile neutrinos could also explain why there's more matter than antimatter in the universe. but most relevant to us. They could pass through Earth completely unimpeded since they don't interact with matter at all under any circumstances. Here's the idea. A regular neutrino turns into a sterile neutrino somewhere in space, slips through the Earth without being touched, and near the surface, transforms back into an active neutrino. That final particle hits the ice, creates a radio signal, and Anita hears it. Problem solved yet again, right? Physicists thought as much, but in science, coming up with clever explanations is not even half of the solutions. You have to check how it holds up with the actual data. Remember how our tau regeneration caused a shower of neutrinos? Well, the problem is that we would certainly see the whole thing if not with Anita, then with the Ice Cube Observatory that is literally a cubic kilometer of Antarctic ice as a detector. The proposed tau regeneration would light it up like a Christmas tree, but it didn't happen on any occasion. Then the sterile neutrino theory. It could easily miss Ice Cube and still trigger Anita on those 2 recorded occasions. But then where are other detections besides Anita? Models showed that if sterile neutrinos were behind this, we'd see them everywhere. Detectors like Ice Cube and Olga have been watching the skies and the ground for years. They were built to capture high-energy neutrinos from every direction, including from below, whatever their origin is. A sterile neutrino powerful enough to produce Anita's signals would produce similar events across multiple experiments. But after analyzing the data, scientists found only several possible matches when there should be at least dozens of similar events over the years. That makes this theory not just unlikely but wrong. So both the tau regeneration and sterile neutrino theory fail, because we didn't see enough other anomalies to support the original 2. So maybe to explain it, we need something completely new. So what if the answer isn't even close to the standard model? I have to admit, this is where things get speculative. Not tinfoil hat speculative, just the kind that makes physicists nervous and excited at the same time, because the Anita anomaly could be exactly the event that changes physics forever. And just like the anomaly in the radioactive decay gave us neutrinos, maybe that balloon caught traces of new undiscovered particles. One theory points to an idea that's been circling the physics world for decades: supersymmetry. And no, it's not when your face is so darn symmetrical that it seems AI-generated. Supersymmetry is a proposed extension of the standard model. It suggests that every known particle has a heavier superpartner that we haven't seen yet: electron, selectron, quark, squark, neutrino, sneutrino. It sounds like Saturday morning cartoon branding, but it's actually serious physics. And don't even get me started on photino and Higgsino. I had enough brain rot memes for a lifetime. So the particle relevant to us is the STAU, the supersymmetric cousin of the tau. And the idea is this: maybe Anita caught the death rattle of a STAU. Here's how it would work. Somewhere in the universe, a high-energy neutrino smacks into something, creating a STAU. That STAU then passes through the Earth unbothered, unabsorbed because of its mass and properties. Then just before reaching the Antarctic surface, it decays. That decay triggers a cascade of particles in the ice, and Anita hears the blast. It sounds really bizarre, but it fits. The energy matches, the direction matches. Even Anita's exclusive detections make sense because of the STAU particle is rare and unstable. You'd only catch it in the strangest places. So why isn't this theory a slam dunk yet? Well, because despite our best efforts, supersymmetry still hasn't shown up at a Large Hadron Collider. We built the most powerful particle smasher in human history, looked for superpartners, and got nothing. No STAU, no squark, no selectron. The whole family skipped the reunion. In recent years, some physicists have started to quietly back away from supersymmetry altogether. Others still believe it's real. We just haven't reached the right energy levels yet. In any case, the STAU theory remains alive, not confirmed, but not dead either, just like your average Schrodinger's cat. And it's not the only exotic explanation on the table. Another theory is even more mysterious and more ambitious. What if Anita, for the first time in history, caught a glimpse of dark matter? You know, the stuff that holds galaxies together and makes up about 85% of all the matter that exists, but we still have no idea what it is. Dark matter doesn't emit or absorb light. It can only warp it in gravitational lenses we see all over the universe. So it's definitely real. But so far, every attempt to detect dark matter directly has failed. But what if, just maybe, Anita got lucky? Some theorists suggest that dark matter particles, if they interact only very slightly with normal matter, might pass through Earth completely undisturbed, just like neutrinos. Then if they decayed near the surface or interacted under extreme conditions, they could produce a burst of energy, a particle shower, and a detectable signal. In fact, this isn't limited to Anita anymore. In 2023, the Kilometer 3 Net Neutrino Telescope located in the Mediterranean Sea detected the most energetic neutrino ever seen, and it also came from a strange direction, not from above, but from the side. In fact, it looks like this ultra-high-energy neutrino passed at least through tens of kilometers of rock and water before entering the detector. And while it's not at Anita levels unplausible, still, according to calculations, this neutrino should have decayed earlier and never triggered the detector in the first place. So a group of researchers in a fresh-made 2025 paper suggested it could be explained by dark matter interactions. According to this, certain types of decaying dark particles, which are sadly too convoluted to explain in K-pop analogies, could produce the exact same picture as both the Mediterranean detection and even the Anita anomaly. Bottom line is, we finally cracked the mystery, or at least got the closest to doing so. And yes, it's just another theory and we need more data to back it up, but the idea is gaining traction. Because here's the thing. When nothing in your known toolkit fits, it's not unreasonable to reach for a new tool, and both the style and especially the dark matter decay hypothesis fit the same basic shape. A rare particle that travels undisturbed through Earth and only makes itself known when it dies violently, spectacularly, and it just happened to be near one of our few detectors. But the point isn't that we found the answer. The point is that it's a wake-up call for physicists to return to the blackboard and start looking for novel solutions. Such things happen only once or twice in a lifetime and almost always lead us to new revelations about the universe. But sometimes history teaches us not to get too excited about weird anomalies. In 2015, astronomers were baffled by a repeating signal from space. It was a fast radio burst that didn't behave like anything we'd seen. For a moment, some people even whispered the word aliens, but what it turned out to be is a glitch, more precisely, reflections from an old NASA satellite Relay 2, bouncing signals back to Earth and confusing the instruments. This mystery wasn't in deep space, it was in our own hardware. And Anita, well, is also a piece of hardware, a balloon that flew for years high up over Antarctica in brutal cold with sensitive equipment incredibly hard to calibrate. Come to think of it, just 2 weird signals in a decade is well within possible glitch margins. So maybe it wasn't a ghost particle, but just a ghost. Of course, scientists wouldn't start buzzing and frantically coming up with explanations if they haven't ruled out some radio interference already. But in the case of that fast radio burst, they also thought they did, and only over a decade later, we saw this mistake. So yeah, maybe Anita glimpsed something that will change physics forever, but at the same time, it still could be some bizarre error yet to be accounted for. Well, what's your gut feeling on this? Share it in the comments.